All right. And here are the notes we're covering today. Business math 5.3. There you go. The notes are in the chat. Okay. Well, let's get started. All right. So on Thursday, we went over graphing linear inequalities. We're going to do the same thing today, but involve linear programming. So what we did last time was we graphed linear inequalities, we found corner points, and now what we're going to do with those corner points is plug them into an objective function. And our job is either to minimize or maximize the objective function. So that's just going to be based on what the question is asking. Okay. So linear programming is a mathematical process that has been created to help management in decision making. The goal is to maximize or minimize a function. For example, we may want to maximize profit or revenue, and we may also want to minimize costs. A linear programming problem is one that is concerned with finding the optimal value, a max or minimum, of the objective function. Z in the form of Z equals AX plus BY, where A and B can't be zero. The objective function for a system of linear inequalities expresses the relationship among the variables involved in the concept to be maximized or optimized using the constraints of the inequalities. Okay, so fundamental theorem of linear programming. If the optimal value of the objective function in a linear programming problem exists, then that value must occur at one or more of the corner points of the feasible region. So once again, we're going to find corner points and plug them into the given objective function. Existence of optimal solutions. If the feasible region for a linear programming problem is bounded, then the maximum value and the minimum value will exist. So remember what it means to be bounded is that once we find our feasible region, can we draw a circle around it? And that's what it means to be bounded if we can draw a circle around it. If the feasible region is unbounded, meaning we can't draw a circle around it, and the coefficients of the objective function are positive, then the minimum value of the objective function exists, but a max does not. And if our feasible region is empty, that means there are no points to satisfy the constraints, then neither the minimum value nor the max value of the objective function exist. Okay. And again, to solve these, we're going to graph them, shade, find corner points, and then plug the corner points into the objective function. And the objective function will usually be given. Everything's going to be given except for the graph and the corner points. Okay. And if you just joined us, once again, here are the notes. I'll post them in here. And also, if you just joined us, so again, this is 5.3, which means Thursday is test 1 review day. So Thursday, come to class if you have questions over the review or any of the homeworks. And then Tuesday will be our first exam. All right. So let's get started. Okay. So solve the linear programming problems by graphing the system of linear inequalities, find the corner points, and test the corner points into the objective function. So it says, example 1, maximize p equals 3x plus 2y. So this is going to be considered the objective function. This is what we have to maximize. Okay. So in order to do that, we have to graph the inequalities. So just like last class, let's go ahead and find the x and y intercepts of each inequality. So I'll call this equation 1, 6x plus 3y, and I'm going to set it equal to 24. And we are going to find the x-intercept and the y-intercept. So x-intercept, we let y equal 0. And we'll get 6x equals 24, divide by 6, and x equals 4. Remember that this creates the point 4, 0. And then the y-intercept, we let x equal 0, and you'll get 3y equal to 24, and divide by 3, and y equals 8. And this creates the point 0, 8. All right, so there's the first one. We have the x-intercept and y-intercept for the first one. Now let's find it for the second one. 3x plus 6y less than or equal to 30. Call this equation 2. 3x plus 6y equal to 30. And find your x-intercept where y equals 0. And you'll get 3x equal to 30, where x is equal to 10. And find your y-intercept, where x equals 0. And you'll get 6y equals 30, where y equals 5. And these create the points 10, 0, and 0, 5. Okay. And then remember that these inequalities, x greater than or equal to 0, y greater than or equal to 0, are the non-negative restrictions. And those are just vertical and horizontal lines. So these are the non-negative restrictions. And basically what that means is you just focus on what's going on in the first quadrant after we graph everything, of course. Okay, so next is we graph after we have these x and y intercepts. So for the blue line, for number 1, we'll do it in blue for the first equation. I have 4, 0, and then I have 0, 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Oh yeah, and again, take note of everything. Remember, based on inequalities, it tells you how your lines are, dashed or solid. And these are all less than or equal to or greater than or equal to. So all these lines will be solid. I'll say solid lines. Okay, and then we just connect the 2 points. However straight you can get it. There we go. It's gonna work for now. So there's the blue line. And now we'll do the red line. So I have an intercept at 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right here. And then I have one at 5. 1, 2, 3, 4, 5. So there's my y-intercept. And again, all solid lines, so just connect. Okay, and now, whoop, I should keep going further, sorry. And that way, there we go. Okay, and now we draw the non-negative lines. So I'm gonna have x equals 0 going down the y-axis. If I could draw a straight line to save my life. And I'll have y equal to 0 going down the x-axis. There we go. So this is y equals 0, and this is x equals 0. Okay, and now we want to shade. So we're just going to pick a test point. And again, we only want to focus on these two lines, the blue and the red one. The x equals 0 and y equals 0 don't really affect us. They just say, hey, you're going to stay in the first quadrant. So just focus on the blue and the red line. And it just so happens that below them is our most popular test point of 0, 0. And we're going to test that into their inequalities above. So I'll say test points. And we're going to take 0, 0 and plug it into both of these inequalities above and see if it holds true. So we'll get the first one, 6 times 0 plus 3 times 0 less than or equal to 24. That gives me 0 less than or equal to 24, which is true. So that means for the blue line, I actually should have did that in blue. Hang on, just so we know which lines we're working with. 6 times 0 plus 3 times 0 is less than or equal to 24. 0 is less than 24, which is true. So I'm going to shade down towards 0, but only in the first quadrant. Okay. And then for the red line, check if it's true. Plug in 0 to the inequality. 3, 0 plus 6 times 0 less than or equal to 30. And we get 0 less than or equal to 30, which is true. Which means, again, we're going to shade down. Okay. So we have our shadings, and now what we want to do is find our feasible region. If we find our feasible region, then we can start listing off corner points. And remember, the feasible region is where our shadings will intersect. So if we look at this, our shadings intersect in this region right here. So right here is where my shadings intersect in this area. That's our feasible region.
And the only time it won't is if there's infinite possibilities.
Exactly. So imagine that all the shadings went up this way. We wouldn't be able to draw a circle around it. Make sense?
Yes, sir.
Okay. So since this is our feasible region, we are going to list off the corner points of it. So we're going to have a corner point here, here, there, and there. 3 of them are easy to see. What's a good? I'll just do it in orange since I already started. So my corner point up there is 1, 2, 3, 4, 5. So that's 0, 5. I already listed 0, 0 down there. My next corner point is going to be at 1, 2, 3, 4, 4, 0. And if you drew your graph perfect, which I did not, then you would be able to easily see this corner point, which looks like it might be at 2, 4. But let's go ahead and just double check by using Desmos. Why not? There we go. And for Desmos, I'm just going to type in these functions here. Let me clear that out. 6x plus 3y equal to 24, and 3x plus 6y equal to 30. And now all we have to do is look at their intersection point. See if I got it right. Zoom in. And these graphs intersect at, what did I say? 2, 4. There you go. That's a nice quick check, right? Good way for us to check our work. Okay, which means we have our corner points, and I'll list them down below. Find your corner points. And we said 0, 5, 0, 0, 2, 4, and 4, 0. Okay, and now back to the notes. We have our corner points of the feasible region, which means now we're going to want to test them into the objective function above. P equals 3x plus 2y. Think I can zoom out for that? Yeah, sure. I got the room. So first one we'll try out is 0, 5. And you'll get P equals 3 times 0 plus 2 times 5, and that'll give me 10. And then we try out 0, 0. P equals 3 times 0 plus 2 times 0, which gives me 0. And then we try out 2, 4. And P gives me 3 times 2 plus 2 times 4. And that's 6 plus 8. That'll give me 14. And then the last is 4, 0. P equals 3 times 4 plus 2 times 0, and we'll get 12. I should have done these in another color. One moment. I'll change that to purple. Why not? Except I didn't do that one, but okay, that's fine. No. There you go. Purple. Okay, now look at our objective values when we plugged in our points and which one is the largest.
2, 4.
2, 4. Good. 2, 4. So 2, 4 is going to be the corner point that gives us the maximum value. 2, 4 maximizes the objective function. And that's how we do it.
If there was negative numbers that are absolute values higher, is that the maximize point?
Say that again.
Like if you had a negative 15, would the max point be 14 or negative 15?
Well, if it was negative 15, then that would be considered a minimum.
Okay, all right.
Yeah. So remember also by the theories on the first page that if you do have a feasible region that's enclosed, a maximum and a minimum exist. So from these numbers, what would be your minimum?
0, 0.
0, 0, right? 0, 0 would be your min.
Cool.
All right, cool. So that's how this works. We're doing everything that we did last time. And just the extra step by taking the corner points and plugging it into the objective function. Any questions on that?
Hi, sir. Just wanted to check in real quick.
Thank you.
Thank you, sir.
All right. Let's do it again. All right. Example 2. Maximize and minimize the objective function p equals 2x plus y. So remember, this is the objective function. So now we want to maximize and minimize this function. And this time we're given 3 equations to graph. Ooh, man. All right. So we'll start by pulling these equations out one by one and finding the x and y intercepts of all of them. So for the first one, we have x plus y equal to 2. And if you go for your x-intercept, y-intercept, x-intercept y equals 0, y-intercept x equals 0. Here you'll get x equals 2. Here you'll get y equals 2. There's my x-intercept and y-intercept, which creates the point 2, 0 and 0, 2. Okay. Pull out the second function, and we get 6x plus 4y equal to 36. 6x plus 4y equal to 36. And again, x-intercept, y-intercept. And for the x-intercept, you'd get 6x equals 36, and x would be 6. For the y-intercept, 4y would equal 36, and y would be 9. Okay. So this makes the points 6, 0, and 0, 9. All right, we still have that third function, so I should have wrote smaller, but I can just do this. Yay. Okay. And then function 3 is 4x plus 2y equal to 20. Okay. And x-intercept, y-intercept. And you'll get 4x equals 20 and 2y equals 20. Here, x equals 5 and y equals 10. And again, 5, 0, 0, 10. Okay. And we have our non-negative restrictions again, x greater than 0, y greater than or equal to 0, but we'll handle those after we graph 1, 2, and 3. So let's go ahead and plot everything that we have. All right, let me see. So 2, 2, oh yeah. And again, since these are all less than or equal to's or greater than or equal to's, these will all again be solid lines. Okay, 2, 0 and 0, 2, and this line. Can I just draw a line? Then move it? Why not? Oh yeah, look at that. Why didn't I think of that before? Something like that. Don't do that. Oh well, close enough. All right, and now that goes like that. That goes like that. And then the next line is 6, 0, and 0, 9. So 1, 2, 3, 4, 5, 6. And then 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. draw another line. Let's see. There we go. And then the last line to draw is at 5, 0, 1, 2, 5, and 10, which I don't have a point for, but we'll put it right above 9 up here. And something like that. There we go. Okay, still not perfect, but it works. Now we will shade. We shade and then we find corner points. Okay, so test points. And looking at all 3 lines, what point is right below them? Our favorite point of
0, 0.
0, 0, right? This point is right below them. Oh, I guess I should draw the non-negative restrictions, right? So here is, do another line. Look at this. It's amazing. There we go. Here's x equals 0, and here's y equals 0. Okay, there we go. So our test point 0, 0. So we tested in all 3 functions. So I'll use the same colors for the same functions. So 0, 0 is going into, actually, I'll just plug it in here. You get 0 plus 0 greater than or equal to 2. And you get 0 greater than or equal to 2, which is false. Which means for the blue line, we're going to shade away from 0, 0. So for the blue line, we get to shade up. Okay. I could keep going, why not? Okay, so blue line, it was false, but now we tried in the red line. And you get 6 times 0 plus 4 times 0 less than or equal to 36. You get 0 less than or equal to 36, which is true. Which means for the red line, we're going to shade towards 0, 0. So down. Okay, and then the last one is less than or equal to 20. So we try it in the green function. You'd have 4 times 0 plus 2 times 0 less than or equal to 20. 0 would be less than or equal to 20, which is good. So for the green line, we also shade towards 0, 0. So many lines. Okay. Now, hopefully it's not too hard to see, but now we have to look for our feasible region. So zooming in, On the first quadrant only, we want it where all the shadings intersect. So all my shadings start to intersect around this point. And then let's see, there's blue and there's red. So right here. And then here. Then I think right here and here. So here's what our feasible region is going to look like. From right here to here. And then there and there. There's our feasible region. So that's where all our shadings intersect at. And now let's list all the points of our feasible region. So we have, that's 1, 2, that's 0, 2. This point, I believe, is 0, 9. This point is 1, 2, 3, 4, 5, 5, 0. And then this point is 2, 0. And all we need is this final point, which, if drawn correctly, looks like 1, 2, 3, 4, 5, 6, looks like 2, 6. But again, let's check. We could be wrong. And this is where green and red intersect. So back to Desmos. I just need the green and the red line because that's their intersection point. So I'm going to do 6x plus 4y equal to 36. And then 4x plus 2y equal to 20. All right, there we have it. Now let's look at their intersection point, and hey, my graph was pretty spot on. Okay, so since the test point was false on the blue line, that's why we shaded up. So if the test point is false, you shade away from the point. But the other two lines became true, so you shade towards the point. So my shadings could have extended further, but I only wanted to keep them in the first quadrant. So since it was false, you shade away. Since they were true, you shade toward 0, 0. Because if it were false, then I would have put my shadings, all of my shadings would have went this way if all of them were false. Okay. Excellent. Good question. Okay, so there's our feasible region. We have all the corner points. I guess I'll list them below again, right here. My corner points are 0, 9, 0, 2, 2, 0, 5, 0, and 2, 6. And now we just have to test them into that given objective function. And we want to find the max and we want to find the min. So we start with 0, 9. And P will be 2 times 0 plus 9, which will give me 9. And then 0, 2 will give me P equals 2 times 0 plus 2. I get 2. And then 2, 0 gives me P equals 2 times 2 plus 0, which gives me 4. 5, 0 gives me 2 times 5 plus 0, which gives me 10. And then 2, 6 gives me P equals 2 times 2 plus 6, which will give me 4 plus 6, which will give me 10. Okay. Now look at our objective values and which one's the minimum.
2 or 0, 2.
0, 2. And which ones are my max?
5, 0 and 2, 6.
Good. There's my max. There you go. Any questions on that?
No, sir.
Looks good. All right. Also, I guess since we're using Desmos, show you something cool. You can put the shadings in here as well. It might get messy, but I can say instead of equal to 36, I can say 6x plus 4y less than or equal to 36, and it will shade it for us. And then same thing here, less than or equal to 20, shades. And then x plus y greater than or equal to 2. And this shows us where all our shadings are, and even our boundary points, corner points. So there's that, 0, 2, 2, 0, 5, 0, 2, 6, and then bam, 0, 9.
So, Professor, what would happen if these were just less than? Would the corner points change?
If all of them were less than?
Yeah, or any of them.
Then, oh, let's see. Well, no, one of them's greater than. So let's say they were all greater than, right?
Okay.
Then if they were all greater than, then my shadings would be going up to the right, which means my corner points then would be at 10, 0, 2, 6, and 6, 0, and that would be it.
For greater than, not greater than, and equal to?
Well, that's for greater than or equal to. Remember, the greater than or equal to are just tells us if we're going to have solid or dashed lines.
Yeah, so if it is dashed, like, are the corner points still found the same way, or that's what I'm
Yeah,
confused.
the corner points will be found the same way still,
Okay.
no matter if it's dashed or solid.
Cool.
All right, cool. But look at that. Desmos is nice, right? There you go. Just got to know how to work it. Okay. All right. And it looks cooler than mine, but whatever. All right. There's that. Last one, y'all. Application problem. So, a furniture manufacturing company manufactures dining room tables and chairs. The relevant manufacturing data are given in the table below. So for the table department, you need 8 hours of assembly and 2 hours of finishing, and the profit per table is $90. For chairs, you need 2 hours for assembly, 1 hour for finishing, and you get $25 per chair. And here are the maximum labor hours per day for assembling tables and chairs. So our job is to create linear inequalities, and we even have to create the objective function for this problem. So let's go ahead and do that based on all this information, which means we're going to need an equation that represents assembly and represents finishing. So for assembly, we are going to write, so this will be equation 1, 8x, so we'll have x represent tables, plus 2y, and we can have up to 400 labor hours per day. So this is going to be less than or equal to 400. And then equation 2 is going to be for finishing. We're going to have 2x plus 1y less than or equal to 120. And now my objective function is going to be how much money do we get for tables and chairs. So my objective function, we'll just call it P, is going to be 90x plus 25y. Does all that make sense?
Yes, sir.
All right, cool. Let's see. Good, good, good. And then I guess before we continue, because I think this problem's like one in your homework, it's going to want you to also make the non-negative restrictions, which are just, we'll call them 3, x greater than or 0, y greater than or equal to 0. So these are the non-negative restrictions. And again, the reason we have these restrictions is because it keeps us in the first quadrant. If we're thinking of business models, in terms of business models, everything should be in the first quadrant. If you go to the second quadrant, the third quadrant, or fourth quadrant, then your business is in trouble because you start dealing with negative numbers. Hence, non-negative restrictions, because everything in the first quadrant is positive. Okay. So we made our linear inequalities. So let's go ahead and solve them. We're going to have to graph them. So for number 1, I'll do this. Oops. So for 1, we're going to make it 8x plus 2y equal to 400. And just like all of them, X-intercept, Y-intercept.
Alexa, what's 400 divided by 8?
You've been using Alexa?
I am right now.
Nice.
Set off my Alexa.
Nice. That's funny. What did Alexa say? 50?
Yeah. She's often right.
I hope so. Oh, you gotta keep it all the same color. Okay, and then equation 2. 2x plus y equals 120. And find x-intercept, y-intercept. Two x equals 120, so x will be 60.
I have a question.
Go ahead.
Is the x and y intercept like always going to be 0, like on that part up there?
Like right here?
Mhm.
Yeah, because remember, if you're ever trying to find an x-intercept, you
Mhm.
always let y equal 0.
Okay.
Because x-intercepts lie on the x-axis, where the value of y is always what number?
0.
0. That's right.
Sweet. Thank you.
Hey, that one was easy. Y equals 120. Okay. There we go. We have x-intercepts, y-intercepts, and now we have to make our intervals appropriate. I think we could go by 20s. I think so. Yeah, let's go by 20s. I'll just rewrite these labels. Intervals 0, 20, 40, 60, 80, 100, 120, 140, 160, 180, and 200. And then same thing up here. 20, 40, 60, 80, 100, 120, 140, 160, 180. We're going to have to make a little extension and add 200. Okay. Perfect. Now, let's go ahead and plot everything that we have. So 50 and 0, it's going to be right between 40 and 60. So right there. And 200, which is up there. And now I'll do my line. Why not? Oh, I even have that. Let's try it out. Oh, it was off by a little. No. I'll get it. It just moves. It doesn't like me. I was better off with the other line. Or not. One day I'll figure it out on this computer. All right. Well, old school. There we go. And then graph the red line. And you have 60 and 120. Yeah. And then just connect those two. There we go. Okay, there's 50 and 200, right? Yeah. Well, I guess it could have gone. Oh, well, that works. Okay, and then I'll draw the non-negative restrictions just to show that we're stuck in these quadrants. There we go. Y equals 0, x equals 0. And now let's go ahead and shade and just focus on the blue and red line. And it just so happens to be that our favorite point of 0, 0 is below them. That looks like 9, 0. So we'll pick test points. We'll use 0, 0 as our test point. So for the blue line, you'd get 8 times 0 plus 2 times 0 less than or equal to 400. And 0 is less than or equal to 400. So that checks out, which means we'll shade toward 0, 0. So we shade this way. And then test it out for the red line. And you'd have 2 times 0 plus 0 less than or equal to 120. And 0 would be less than or equal to 120. So those all check out. So for the red line, we would shade towards 0, 0 as well. Because I could go past that. Why not? That's good enough. Like I said, we only need to be in the first quadrant. So once again, we look at our graph, only the first quadrant, and we look for the feasible region where our shadings intersect. And where they start to intersect looks like about this point, 0, 0, this point, and right here where they intersect. So this is our feasible region, which can be enclosed. Okay, so since that's our feasible region, let's start listing off the corner points. One of them's labeled already as 0, 0. The next corner point is going to be 50, 0. And then 0 and 120. And if my graph is correct, that looks like 20 and, or maybe not. Maybe I'm just way off. Let's see. 0, 120, 0, 0, 50, 0. And that intersection point. Yep, we're going to have to double check that one because I think my graph is a little bit off. Because it's right where those intersect. 0, 50, 50 and 200 and that. Yep, let's go with Desmos. My graph is not that great. So get rid of that, get rid of that, get rid of that. And 8x plus 2y equal to 400. And then 2x plus y equal to 120. And I'm gonna have to zoom. There we go. And they intersect at 40, 40, which means my graph is definitely way off by scale somehow. Somehow that happened. 60, 120, and 40 and 40. Wow. Okay. Well, this point is 40, 40. That's why we always double check, because sometimes our drawn graphs are not that great, or maybe just mine. Okay, cool. Well, back to the notes. We have our corner points, and now we want to test them. Oh, this is still A. We haven't even moved on to B and C yet. So now we want to test our corner points into the objective function and see which amount will give us a maximum profit. So we have 0, 0, and then we have 50, 0, 0, 120, and 40, 40. And plug them into the objective function we made. 90 times 0 plus 25 times 0 gives me 0. 90 times 50 plus 25 times 0 gives me 4,500. And then 90 times 0 plus 25 times 120 gives me 3,000. And then 90 times 40 plus 25 times 40. That gives me 4,600. So, what amount of table of chairs will give us the maximum profit?
40, 40, or the 4,600 one.
There you go. Okay, cool. All right. And then last two questions. B says, discuss the effect on the production schedule and the maximum profit if the profit on a chair decreases to $15. Oh boy. So all this wants us to do is just create a new objective function, because chairs were originally $25 a chair, but now they're going to be reduced to 15. So our new objective function would become P equals 90x plus 15y. So, I mean, we could plug in numbers. Maybe that's what it wants us to do, but we can just use common sense here and say, what would happen if you reduce the profit on your chairs? What's going to happen to your maximum profit?
It's going to reduce your maximum profit.
That's it, right? So if we go to $15, then your maximum profit is going to decrease. That's it. And if you made your chairs cheaper, that means your production schedule might increase, right? Meaning you're just going to lose out on money because now you're paying more in hours. So again, these are just kind of think about it. And then C says, discuss the effect on the production schedule and the maximum profit if the profit on the chair increases to $40. So if we make this P equals 90x plus 40y, well, now we increase the amount of a chair. We're going to make $40 in profit off of chairs instead of 25. This means that our profit will what?
Increase.
That's it. Max profit increases. Max profit increases. Okay. And that's it.
I have a question on B.
Go ahead.
For the objective, if you're decreasing, how come it's not like a negative right there for the 15y?
Well, because we're saying, because profit was 25 for a chair, and all this problem is saying is that now chairs are $15.
Oh, okay, okay,
That's all it's saying.
okay.
Make sense?
Hmm?
Okay. All right. Well, guys, that is it. That is 5.3, which finishes up our lectures before the first exam. So like I said, Thursday is just a review day. So come if you have questions, if you have anything over homework or the review. If you don't, then don't worry about coming on Thursday. And then Tuesday, you will take the exam.